few gemstones on Earth are studied for something unusual. Not their beauty, not their rarity, but their chemistry. Inside certain crystals are combinations of elements that scientists normally encounter in laboratories. Tungsten, zirconium, boron, beryllium, locked into natural structures formed deep underground. Some of these minerals interact with light in unusual ways. Some contain metals used in modern electronics, and some possess crystal frameworks so rare that researchers still examine them to understand how such structures formed at all. These stones were never created for technology, but in a strange way, they resemble materials engineers are still trying to design. In this countdown, we explore 10 remarkable gemstones whose unusual chemistry has captured the curiosity of scientists and collectors alike. Starting with a crystal that quietly changed how precision optics are built. Ranked 10th, fluorite. Most gemstones earn their place in collections for beauty. Fluorite earned attention for something else entirely. At first glance, it hardly looks like a technological material. The crystal forms in soft cubes and octahedrons, often glowing with shades of violet, green, or icy blue. Compared to diamonds or sapphires, fluorite feels almost delicate. On the Mohs scale, it ranks only 4, far too soft for most jewelry. For decades, that softness caused gem buyers to overlook it. Scientists did the opposite, because fluorite possesses a property that changes how certain optical systems are built. Its crystal structure allows light to pass through with extraordinary purity, particularly in ultraviolet wavelengths. In most materials, ultraviolet light scatters and distorts. Fluorite behaves differently. Under the right conditions, it transmits light with remarkably low dispersion and minimal internal interference. That single characteristic quietly made fluorite valuable far beyond the gemstone world. High-precision optical systems, the kind used in advanced microscopes, space optics, and semiconductor manufacturing equipment, require materials capable of transmitting extremely precise wavelengths. Even microscopic distortions can ruin an image or corrupt data. Engineers searching for that level of clarity discovered that nature had already solved the problem. Massive fluorite crystals had been forming underground for millions of years. Large pure specimens from places like Weardale in England, the Illinois-Kentucky fluorspar district in the United States, and the Alps revealed crystals with optical qualities that synthetic materials struggled to match in earlier decades. Today, specially grown fluorite crystals are used inside some of the world's most advanced optical equipment, but the natural versions still fascinate mineral collectors. Not because they power machines, but because they demonstrate something deeper about geology. In the right chemical environment, deep underground, simple elements like calcium and fluorine can organize into a crystal lattice so clean that it becomes useful for technologies humans would not invent for millions of years. In other words, long before engineers designed ultraviolet optics, the planet had already been producing a material capable of supporting them. And fluorite is only the beginning. Because deeper in the mineral world, there are crystals whose chemistry is far stranger. Minerals containing elements, structures, and optical behaviors that researchers are still trying to understand. Some appear in only a handful of deposits on Earth, and the next gemstone on this list isn't just rare. It hides a metal that quietly powers some of the most extreme industrial technologies ever built. Ranked 9th, scheelite. In the early 20th century, prospectors searching for tungsten carried an unusual tool into the mountains. Not a hammer, not a drill, an ultraviolet lamp. At night, certain rocks would suddenly glow a brilliant electric blue, a signal that something valuable was hidden inside the stone. That glow belonged to scheelite. Unlike most gemstones, scheelite sits directly on the border between the mineral collector's cabinet and the industrial world. Its chemical structure, calcium tungstate, contains one of the most strategically important elements in modern engineering. Tungsten. Tungsten is a metal built for extreme environments. It holds the highest melting point of any commonly used metal, remaining stable at temperatures where steel softens and aluminum disappears entirely. Its strength under heat made it essential for early industrial tools, high-performance alloys, and specialized electronic components. And for much of the 20th century, one of the primary natural sources of tungsten came from crystals of scheelite. The mineral forms when tungsten-rich fluids move through limestone or metamorphic rock deep underground. Over time, calcium and tungsten combine into transparent to honey-colored crystals, sometimes forming sharp pyramidal shapes that mineral collectors immediately recognize. Under normal light, scheelite can appear surprisingly modest. Under ultraviolet light, it transforms. The crystal emits a vivid blue fluorescence, a property that once allowed geologists to scan entire mountainsides for tungsten deposits after sunset. In darkness, a rock face containing scheelite could suddenly light up like a hidden constellation. For mineral collectors today, scheelite holds a special fascination. It represents a rare intersection where a gemstone quality crystal is also a direct carrier of an industrial metal that shaped entire technological eras. Specimens from China, Pakistan, Austria, and parts of the western United States can produce beautifully formed crystals that glow dramatically under UV light. Many of those crystals will never become jewelry. Instead, they remain exactly as nature created them. Quiet reminders that the minerals admired in display cases often carry elements that help build the modern technological world. And deeper within Earth's crust, there are crystals whose significance goes even further. Not because they contain industrial metals, but because they preserve a record of the planet itself, stretching back billions of years. The next gemstone on this list does exactly that. Ranked 8th, Zircon. Long before diamonds formed in the Earth's mantle, before continents stabilized, before complex life appeared in the oceans, a crystal known as zircon had already begun forming deep inside the planet. Some zircon crystals discovered in Western Australia are over 4.4 billion years old. That makes them among the oldest known materials ever found on Earth. Older than most mountains, older than most rocks. In geological terms, zircon is less a gemstone and more a time capsule. Its crystal lattice is incredibly stable. When zircon forms, tiny amounts of uranium atoms can become trapped inside the structure. Over immense spans of time, those uranium atoms slowly decay into lead at a predictable rate. Geologists discovered that this process acts like a natural clock. By measuring the ratio between uranium and lead inside a zircon crystal, scientists can determine the age of the rock in which it formed, sometimes with astonishing precision. This technique, known as uranium-lead dating, has become one of the most powerful tools for understanding Earth's history. Entire timelines of continental formation, volcanic activity, and planetary cooling have been reconstructed using zircon crystals no larger than a grain of sand. But zircon is not just valuable to geologists. Its unusual chemistry has also attracted attention from material scientists. The mineral structure, zirconium silicate, contains zirconium, an element prized for its resistance to heat and corrosion. Zirconium-based materials are used in environments where extreme stability matters, including high-temperature ceramics and specialized industrial components. In laboratory research, zircon-derived materials are also explored for advanced ceramics, radiation-resistant structures, and optical applications. Nature, once again, produced a crystal with properties engineers would later find useful. Collectors admire zircon for different reasons. Fine specimens from Cambodia, Sri Lanka, Myanmar, and Tanzania can produce brilliant gemstones with exceptional fire and color, ranging from golden honey tones to icy blues created through heat treatment. Yet behind that beauty lies something far more profound. Every zircon crystal is a fragment of deep planetary history, a tiny structure that survived billions of years of geological change while preserving chemical information scientists can still read today. In a world of gemstones celebrated for rarity or beauty, zircon stands apart for a different reason. It is one of the few minerals capable of recording the story of the planet itself. And the crystals appearing next on this list reveal something equally fascinating. Not about the age of Earth, but about the strange optical physics that can emerge from a mineral lattice few people expect. Ranked 7th, Sphalerite. Place a well-cut sphalerite under a strong beam of light, and something unusual happens. Instead of a single flash of brilliance, the crystal erupts into fragments of color. Reds, oranges, greens, and yellows scattering across the surface almost faster than the eye can follow. The effect can feel exaggerated, almost unnatural, because the crystal is bending light far more dramatically than most gemstones ever could. Sphalerite possesses one of the most extreme optical properties found in natural minerals: extraordinary dispersion. When light enters the crystal lattice, it separates into its spectral components with remarkable intensity. Even diamonds, famous for their fire, display significantly lower dispersion than sphalerite. Yet despite this astonishing visual performance, sphalerite almost never appears in jewelry stores. The reason lies in the crystal's physical structure. Sphalerite is composed primarily of zinc sulfide, a mineral that forms deep within hydrothermal environments, where zinc-rich fluids move through fractures in surrounding rock. The atomic arrangement responsible for its optical fire also creates a material that is relatively soft and brittle. Cutting sphalerite into gemstones requires precision and patience. Wearing those stones daily would almost guarantee damage. As a result, most sphalerite crystals remain in the world of mineral collecting rather than jewelry. But the mineral's chemistry has long attracted attention beyond collectors. Zinc sulfide is a compound that researchers have studied for decades because of its interaction with light and electrical energy. In laboratory settings and industrial materials science, variations of zinc sulfide have been explored in infrared optics, phosphorescent materials, and early semiconductor technologies. Long before many synthetic optical materials existed, scientists were already experimenting with the unusual optical behavior of zinc sulfide compounds. Nature had already demonstrated what the crystal lattice could do. Collectors encountering transparent sphalerite specimens, particularly those from Spain, Mexico, and parts of Eastern Europe, often react with surprise. When properly cut, the gemstone produces an intensity of spectral fire that seems almost excessive, as if the crystal is amplifying the physics of light itself. Few minerals reveal optical physics so dramatically, and deeper in the mineral world, some crystals contain elements far more familiar than zinc, elements that quietly sit inside everyday electronics. The next gemstone on this list forms from one of the metals that made modern circuitry possible. Ranked 6th, Cassiterite. Inside almost every electronic device, there is a metal most people never think about. It does not appear on the surface of a smartphone. It is not visible on a circuit board. But without it, modern electronics would simply stop working. That metal is tin. And deep inside the earth, one of the minerals that carries it is a gemstone-quality crystal called cassiterite. Cassiterite is the primary natural ore of tin, a simple but crucial metal used for centuries in alloys, coatings, and eventually electronics. Today, tin plays an essential role in the tiny metallic joints known as solder, which connect electronic components on circuit boards. Every computer, smartphone, satellite system, and medical device relies on thousands of these microscopic connections. Without tin, those circuits cannot function. And in nature, much of that tin begins its geological journey inside cassiterite crystals. The mineral forms in high-temperature hydrothermal environments where tin-rich fluids move through fractures in granite or metamorphic rock. Over time, the tin combines with oxygen to create tin dioxide, forming dense crystals that can range in color from deep brown and black to rare transparent honey tones. Most cassiterite appears opaque and industrial, but occasionally nature produces crystals clear enough to facet into gemstones. These rare gem-quality stones reveal something unexpected. Cassiterite has an extremely high refractive index, allowing it to interact with light in ways that rival some of the most brilliant gemstones. When properly cut, the crystal can produce sharp flashes of internal reflection that surprise even experienced collectors. Despite this optical potential, cassiterite rarely enters the jewelry market. Its role in industry has always overshadowed its beauty. Major deposits have historically been found in regions such as Bolivia, China, Myanmar, and parts of Central Africa, where cassiterite mining supplied the tin that helped build modern electronics. Collectors, however, see the mineral differently. In mineral cabinets, cassiterite crystals represent a strange intersection between geology and technology. A gemstone that carries within it the raw material responsible for connecting the circuitry of the modern world. It is a reminder that some of the minerals admired in display cases are not only beautiful geological formations, they are also part of the invisible infrastructure behind everyday technology. And further down this list are crystals whose chemistry becomes even more unusual. Minerals containing elements so rare and structures so complex that scientists still study them in laboratories today. One of those crystals appears next. Ranked fifth, Phenakite. In mineral laboratories, certain crystals attract attention not because they are rare, but because they behave unusually well under scientific instruments. Phenakite is one of them. At first glance, the stone appears almost deceptively simple. Transparent crystals often resemble quartz or colorless topaz. Clean, geometric, and sometimes nearly invisible when placed against light. But inside its structure lies something that researchers find extremely interesting. Phenakite is composed of beryllium silicate, forming a crystal lattice that is both exceptionally stable and remarkably transparent to certain wavelengths of light. That combination has made the mineral a subject of quiet curiosity among mineralogists and material scientists for decades. In controlled environments, crystals with similar chemical frameworks are sometimes examined for their optical clarity, structural stability, and interaction with high-energy light sources. The reason is simple. Some crystal lattices behave in ways that allow light, energy, or signals to move through them with unusual precision. Understanding how those structures work can sometimes help scientists design synthetic materials with similar properties. Nature occasionally provides the blueprint first. Phenakite crystals grow in pegmatite deposits, geological environments famous for producing minerals with unusual chemical compositions. In these pockets of slowly cooling magma, rare elements such as beryllium, lithium, and tantalum can concentrate and form crystals that almost never appear in ordinary rock formations. Over long periods of geological time, those conditions can produce remarkably clear phenakite crystals. Some of the finest specimens have been found in Brazil, Madagascar, Russia's Ural Mountains, and Myanmar, where transparent crystals large enough for fast seeding occasionally emerge from pegmatite veins. Collectors prize these stones not only for their clarity, but also for their rarity in the gemstone market. Even well-cut phenakite gemstones are relatively unknown outside specialized mineral circles, yet the mineral continues to interest researchers for another reason. Beryllium-bearing crystals often possess exceptional rigidity at the atomic level, allowing their internal structures to remain stable under conditions that might distort other materials. This kind of structural stability is one of the properties scientists often investigate when studying new optical or high-performance materials. Phenakite may never become a widely used technological material, but its crystal structure represents something scientists frequently search for. A naturally occurring example of a lattice that behaves with remarkable precision. In other words, a mineral that quietly demonstrates how certain atomic arrangements can produce unusual physical behavior. And deeper in the mineral world, some crystals push that idea even further, because the next gemstone on this list forms from a chemical structure so rare that only a handful of deposits on Earth have ever produced it. Ranked fourth, Jeremejevite. In 1883, Russian mineralogists examining crystals from the mountains of Siberia encountered something they could not immediately classify. The crystals were slender, transparent, and sharply formed, but their chemistry did not match any known mineral species. Further analysis revealed a structure unlike most gemstones. The mineral contained an unusual combination of aluminum and boron, arranged into a crystal lattice that rarely appears in nature. The new mineral was named Jeremejevite. From the beginning, Jeremejevite occupied an unusual place in mineralogy. It was neither common enough to become an industrial material, nor well known enough to enter the jewelry market. For decades, the mineral existed mostly in scientific papers and small museum specimens. Only later did collectors realize how remarkable the crystal truly was. Transparent Jeremejevite crystals possess a clarity and color that can rival far more famous gemstones. Pale blue and nearly colorless crystals, when cut carefully, produce elegant gemstones with a cool, glass-like brilliance. Yet their true fascination lies in the chemistry hidden inside the lattice. Jeremejevite belongs to a class of boron minerals, compounds that scientists often examine because of how boron atoms behave inside crystal structures. Boron-based materials can exhibit unusual optical and electronic properties, which is why synthetic boron compounds are sometimes studied for specialized optical technologies. In nature, however, such structures form only under extremely rare geological conditions. Jeremejevite typically grows in pegmatites, geological environments famous for concentrating rare elements. These slowly cooling pockets of mineral-rich magma allow unusual chemical combinations to crystallize, sometimes producing minerals that appear nowhere else on Earth. Even within pegmatites, Jeremejevite remains scarce. Some of the finest crystals have been discovered in Namibia, Afghanistan, and Russia, where long prismatic crystals occasionally emerge from granite veins. When transparent enough, they can be cut into gemstones that remain almost unknown outside advanced mineral collections. For collectors, Jeremejevite represents something more than rarity. It is a reminder that Earth's geology sometimes assembles chemical structures that scientists would struggle to design intentionally. And deeper in the mineral world, there are crystals where the chemistry becomes even more complex. Minerals built from multiple rare elements that combine inside a single lattice. One of those crystals appears next. Ranked third, Grandidierite. In some parts of the world, miners occasionally pull crystals from rock that even experienced gemologists hesitate to identify at first glance. The color alone can be confusing. Grandidierite often appears in shifting tones of blue, green, and teal, sometimes within the same crystal. Under different lighting conditions, the stone can seem to change character entirely, moving between oceanic blue and deep green, depending on how light travels through its structure. That optical behavior is known as pleochroism, but the real complexity lies deeper inside the crystal. Grandidierite is composed of a remarkably intricate chemical formula combining magnesium, aluminum, boron, oxygen, and silicon. The resulting crystal lattice is far more complicated than the structures found in most common gemstones. In mineralogy, complexity often signals rarity. For a mineral to form, the surrounding environment must supply the correct elements in the correct proportions, while pressure, temperature, and cooling conditions remain stable long enough for crystals to grow. When several uncommon elements must align simultaneously, the number of places on Earth where that can happen becomes extremely limited. That is exactly what happened with Grandidierite. For much of the 20th century, the mineral was known only from Madagascar, where opaque specimens were first discovered in 1902 and named after French explorer Alfred Grandidier. Those early samples fascinated mineralogists, but were not suitable for gemstones. Transparent crystals seemed almost non-existent. Then, more than a century later, new discoveries in Madagascar revealed something unexpected. Small pockets of crystal had formed with remarkable clarity. Suddenly, a mineral once studied mostly in geological collections entered the gemstone world, though only in extremely limited quantities. Faceted Grandidierite gemstones remain among the rarest transparent gems available to collectors. But what continues to interest scientists is the crystal's internal architecture. Complex borosilicate structures like Grandidierite demonstrate how multiple elements can organize into stable lattices under very specific geological conditions. These kinds of structures often attract attention in mineralogical research because they reveal how atoms arrange themselves when unusual combinations of elements meet deep within the Earth. In other words, Grandidierite is not just rare. It represents an example of how nature occasionally assembles complex crystal frameworks that scientists continue studying to understand how such structures form. Collectors see something slightly different, a gemstone whose color, rarity, and geological story place it among the most intriguing modern discoveries in mineralogy. And even Grandidierite is not the rarest crystal on this list, because the next mineral exists in quantities so small that many collectors will spend their entire lives studying gemstones without ever seeing one in person. Ranked second, Serendibite. In the world of mineral collecting, there are stones that are rare, and then there are stones that most collectors will never see at all. Serendibite belongs to the second category. For much of the 20th century, the mineral existed almost entirely as a scientific curiosity. It was first identified in Sri Lanka in 1902, where a few small samples revealed a crystal composition so unusual that mineralogists struggled to place it within existing mineral groups. The name itself comes from Serendib, the ancient Arabic name for Sri Lanka. But after that initial discovery, the mineral seemed to disappear from the geological record. For decades, only a handful of specimens were known. Unlike many gemstones that eventually appear in new mining regions, Serendibite remained almost mythical, a mineral mentioned in mineralogical catalogs but rarely encountered in reality. Many gem collectors knew the name without ever expecting to see the stone itself. Part of the mystery lies in the mineral's chemistry. Serendibite forms from a complex mixture of calcium, magnesium, aluminum, boron, silicon, and oxygen, creating a crystal lattice that requires a very specific geological environment to develop. Those conditions appear to occur only in rare metamorphic settings, where unusual combinations of elements are present at high temperatures and pressures. When the right conditions finally align, the result is a crystal with a deep, almost mysterious appearance. Transparent Serendibite gemstones often display rich blue-green to nearly black tones, sometimes revealing flashes of internal light when viewed under strong illumination. Because so few crystals are suitable for cutting, faceted Serendibite gemstones remain among the rarest gems in existence. Even today, only small deposits have been confirmed, primarily in Sri Lanka and Myanmar. For collectors, Serendibite represents a very different type of rarity. It is not simply scarce. It is the kind of mineral that sits at the edge of the known gemstone world. Rarely mined, rarely seen, and almost never encountered outside advanced collections or specialized auctions. And yet the mineral also represents something else. Its complex chemistry shows how unusual combinations of elements can organize into stable crystals under extreme geological conditions. Each specimen is a reminder that the Earth occasionally produces minerals so rare that entire generations of collectors may pass without ever seeing one. But even Serendibite does not reach the final level of rarity, because the gemstone at the top of this list spent decades as one of the most mysterious minerals ever discovered, a crystal so scarce that for years, only 3 specimens were known to exist on the entire planet. In first place, Painite. In 1951, a small reddish crystal was discovered in Myanmar and sent to a laboratory for identification. At first, mineralogists believed it might be a known gemstone that had simply been misidentified in the field. The color resembled ruby, and the crystal structure appeared somewhat familiar. But the analysis quickly revealed something unexpected. The mineral did not match anything in the scientific record. Further examination showed a crystal structure containing an extremely unusual combination of elements, including calcium, zirconium, aluminum, boron, and oxygen. No known mineral species share that arrangement. The stone represented an entirely new mineral. It was eventually named Painite after the British gem dealer Arthur C.D. Payne, who first brought the specimen to scientific attention. But what made Painite extraordinary was not just its chemistry, it was its scarcity. For decades after its discovery, only 3 crystals were known to exist anywhere on Earth. Museums and mineralogists studied them intensely, trying to understand how such a complex mineral could form at all. The combination of elements required to build the crystal lattice appeared so unlikely that many geologists assumed the mineral would remain one of the rarest substances ever discovered. For years, Painite held that reputation. Collectors often referred to it as the rarest gemstone on Earth. Later discoveries in Myanmar revealed that Painite was not quite as singular as once believed. Additional crystals were eventually found in the Mogok region, a geological environment famous for producing unusual mineral combinations. Even so, transparent crystals suitable for gemstones remain extremely scarce. Most specimens appear as dark reddish-brown crystals with a hexagonal shape, often opaque or only slightly translucent. Only a small number have ever been cut into faceted stones, but rarity alone is not what fascinates scientists. Painite's crystal structure represents one of the most complex borite mineral frameworks known in natural geology. The precise conditions required to assemble its elements, including the presence of zirconium within the structure, appear to occur only under very specific geological circumstances. In other words, Painite is not merely rare. It is the product of an extremely unlikely alignment of chemical ingredients deep inside the Earth. For collectors, the mineral represents the ultimate expression of geological improbability, a crystal whose existence once seemed almost impossible, and yet nature produced it, hidden for millions of years inside a remote mountain region, waiting to be discovered. A reminder that even today, the Earth still holds minerals capable of surprising the scientific world. Some gemstones are rare, some are beautiful, but a few reveal something far more interesting. The strange ways nature can arrange elements into crystal structures scientists are still trying to understand. Which gemstone on this list surprised you the most? Because sometimes the most fascinating part of a gemstone isn't its value. It's the chemistry hidden inside the crystal.